long December, and there's reason to believe maybe this year will be better than the last. And it's one more day up in the canyons, and it's one more night in Hollywood. And if you think that I could be forgiven, I wish you would. Hello everybody, welcome to this week's edition of Video Notes from Mr. Flugen's AP Chemistry class. That's right folks, this is for AP Chem. And we are going to be talking about Gibbs free energy, kind of our last installment in our thermodynamics unit. Okay, and the big thing here is figuring out this thermodynamic favorability, which means how likely is it that this reaction will happen on its own. So let's get started. So if you're doing these video notes early in the week here, it may not make a whole ton of sense, but basically what we're talking about is this: how can we figure out if reactions are thermodynamically favored? That means that they are going to proceed forward on their own rather than needing some kind of energy input or stimulus to make them happen. All right. Now, what we're going to be talking about in class at some point this week, if you're doing this early in the week, is we're going to be talking about this delta S, which is entropy, right? Which is the disorganization or chaos in a system, or or in this case, the universe. Okay. Here in this video notes lecture, we'll be talking about delta G, which is called the Gibbs free energy. Alright, so here we have our Gibbs free energy equation. This is one way for us to calculate the Gibbs free energy of a reaction or a system. So here we have, of course, delta G is our symbol for Gibbs free energy. Kind of makes sense, right? Here we have our enthalpy, right? Our change in energy of the system, okay, our heat. We also have our temperature in kelvins, of course, and last but not least, our entropy change, which basically means the change in inner disorder for that system. Now, when we calculate delta G, this is one of the things you're really going to need to know. It's this, right? If our delta G is negative, if it's less than 0, then the reaction is thermodynamically favored, which means that reaction is going to proceed forwards without any energy being put into the system. So here's what these things actually mean, right? We have our delta G, which is the maximum amount of energy that can be used to do work. So when the system changes and does work on the things around it, right? We have the energy transfer to feed, of course, which is our enthalpy, and our energy used to create disorder. And remember, things are going to generally tend towards more disorder, right? And again, if delta G is negative, the reaction's thermodynamically favored. It's going to proceed. All right, so we're going to look at two methods for finding Gibbs free energy in these video notes. First one uses this equation here, and we can derive the parts of this equation in many ways. You know, we can find delta H using calorimetry or Hess's law or enthalpy of formation, all things we've talked about this week, right? We can also calculate our entropy, right, using entropy values from our tables. And then last but not least, okay, we can calculate delta G using this equation, okay? And then we're also going to look at calculating delta G from the change in formation of Gibbs free energy formation values, which we can find in our tables in our textbooks. All right, folks, so let's go ahead and apply this equation and calculate delta G. The first thing I want you to look at, though, is read through the data we have for the problem, right? Delta H is negative 218 kilojoules, and delta S is negative 765 joules per Kelvin at 32 degrees Celsius. Well, two things I want you to notice. First is this. This is joules, and that's kilojoules. That's a problem. We need to convert that, right? Second thing is this. Don't use the Celsius values. Remember, we're always going to use values in kelvins when we do our calculations. So let's do this first. I'm going to change those joules, so negative 765 kilojoules, or joules, excuse me, per Kelvin. That's equal to negative 0.765, right, kilojoules per Kelvin. Remember, the conversion is just 3 decimal places, right? Okay, so let's plug things into our equation here, right? Delta G is equal to negative 218 kilojoules in heat transfer, right? Take away this guy here is 305 kelvins, right, times our negative 0.765 kilojoules per Kelvin. Okay, now once you crunch out all the numbers there and stuff, you end up with this. You end up with delta G equal to 15 kilojoules. And if you want to get all sig figs on me, 15.0. All right, so that means that the answer to this question is this, right? No, it is not thermodynamically favored. We have a positive Gibbs free energy. All right, folks, so here's the next step, right? What happens when we change temperature? So at what temperature does that reaction that we just calculated for become thermodynamically favorable? So we're going to assume, because we got 15 kilojoules here, right? We're going to assume that delta H and delta S stay the same. We're going to do this, figure out, okay, what happens when we change the temperature? Now, think about this, right? Our delta G is equal to delta H, which in this case is negative, right? Minus our temperature, which is, of course, positive because it's kelvins, and our delta S, which is negative. So here we're going to have minus a minus, right? Right here. So that means that our entropy and temperature are always going to be positive in this case. And our delta H, of course, is negative. We want to find a negative delta G, right? So that we can figure out it's thermodynamically favored. So is the temperature going to need to go up or down to get thermodynamically favorable? In this case, we need to find this, that the temperature goes down. So here I just took a shot and I said, okay, what if the temperature was reduced by 15 kelvins to 290? Well, when I calculate that out, I get 4 kilojoules. Okay, we need to go a little lower. So I tried this. I did a couple of trials and I found this. 284 kelvins gives us a negative 1 kilojoules. So that tells us this. If we can decrease the temperature 21 kelvins to 284, we can make this reaction thermodynamically favorable. Again, folks, I just used this thing right here, okay, and plug different values in for T. So here's kind of some trends to think about, right? Temperature and thermodynamic favorability, all right? Basically, here's the deal. If delta H is negative and our entropy is positive, we're going to have thermodynamic favorability all the time, no matter what temperature it is, all right? However, if delta H is positive but our entropy is negative, we're going to have not thermodynamically favorable. And then you can see here the chart continues. If we have both negative, it's dependent on temperature, just like we saw on the last thing, right? And as we showed, at lower temperatures, that means we're going to be thermodynamically favorable. If we have both positives, right, that's going to be thermodynamically favorable at high temperatures. Okay, folks, so let's look at this problem here. We want to look at the thermodynamic favorability of a reaction. So we've got a change in enthalpy that is negative, and we have a change in entropy that is positive. Now, if we keep that equation in mind, right, with Gibbs free energy, that delta H minus temperature times delta S, then we know this, right, that our answer should be yes, it is thermodynamically favorable at all temps. And that is because of this, right? If we have a negative delta H and a positive delta S, then our Gibbs free energy, our delta G, is going to be negative, which means that is thermodynamically favorable. Okay, so let's look at our second way of calculating our Gibbs free energy, our change in Gibbs free energy, and that is to use the delta G of formation values. Okay, again, like all of these, they can be found in tables in your textbooks. Okay, and the equation is very similar to other ones that we have used. All right, folks, so just like our change in enthalpy values and our change in entropy values, right? This is basically the change in free energy when you have 1 mole of a compound, right? And keep this in mind, right? The delta G of formation for an element in its standard state is 0. So here's our reaction. Should look really familiar. Okay, you can do this same thing with formation, with entropy formations, and as well as enthalpy formations. And here we have Gibbs free energy of formations. Again, these values can be found in the appendix in your back of your textbooks. All right, folks. Well, let's check out this problem here, where we're going to find the free energy of formation, free energy from this reaction for thermite. Okay, using our free energy of formation. So here's our equation. Should look familiar, and we're just going to set it up like this. So here we have our equation written out, and this guy right here is for the iron up here. So remember, it's the mole coefficient, right, times the formation, which in this case for pure iron is 0. And over here I wrote it in just for the sake of you guys seeing that happen, right? Remember, the free energy of formation for things that are in their elemental state is 0. So if we do our math, we end up with an answer of negative 835.5 kilojoules per mole is our free energy of formation problem right there. So pretty simple to use. We've used lots of equations like this. This looks familiar, doesn't it? Okay, something that you need to keep in mind is this. Just because something is thermodynamically favored does not mean that it is fast. All right? Rate of reaction is determined by something else called kinetics and not thermodynamics. Thermodynamics just tells us if they are going to happen on their own, right? Kinetics, which we will study later, will tell us how fast they'll happen. So, for example, we know this, that iron rusting is a thermodynamically favorable process, but it may take years and years for something that is made out of iron to completely rust away. So, although these happen on their own, they may not happen fast. The other thing that we need to think about is this, is when our delta G is greater than 0. That means we do not have a thermodynamically favorable reaction, right? And so, in order to make these reactions happen, we can bring in some external energy. And that can drive those reactions and make them happen. For example, the photosynthesis, the conversion of CO2 and water into glucose, okay? That is not a thermodynamically favorable reaction. You can see our delta G is a huge amount. But if we bring on in an energy source, for example, photons, okay, we can drive that reaction forwards despite the fact that it's not thermodynamically favorable. All right? So, same thing here, right? When we're using a battery, right, to drive that battery backwards, okay, and recharge it, that is a chemical reaction that's not thermodynamically favorable. But if we use electricity, we can make that happen. Well, thanks for tuning in, folks. Hope you have a good day, and I'll see you in class on Friday. Bye-bye.